we are here to present CacheWarp software-based fault injection used in selective state reset. And I'm Ruiyi Zhang, a PhD student from CISPA.
And I'm Youheng Lu, a security consultant at Schwarz.
So this is a joint work also with Lukas, Daniel, Lorenz, Andy, and Michael. So first, I want to mention that this is an attack paper, and CacheWarp is the first attack fully break integrity of SEV-SNP. And we released this vulnerability last November, and back then CacheWarp received a lot of attention. However, much of the feedback that we have heard were like, this sounds too low level to me, and I cannot really understand it. Well, actually, I mean, it's very straightforward. CacheWarp basically stands for cache and warp. However, before I talk about something about cache, I want first to start with memory, because memory has been well explored, with many research papers and vulnerabilities. So I assume that you guys are more familiar with memory. So first, what do we have in memory? First, we have the code. Before the CPU wants to execute something, it has to fetch the code, and that's from the memory. And next, of course, we have the data, like a variable, either from stack or heap. If the CPU wants to process this value, it has to fetch them from the memory. However, compared to the execution speed of modern CPUs, the accessing a DRAM is very, very slow, and it has already become a bottleneck. So to address this issue, our modern CPU has a much smaller but faster buffer, which is known as cache. And in most cases, memory reads and writes are first loaded into the cache and only updated there. And only until there are some memory activities, either from your following codes or from some other memory activities from other process or from other cores, occupy the cache as well. And then your content in the cache gets evicted and updated in the memory in the end. So CacheWarp destroys this state, erasing everything inside the cache, just like a wormhole. So how do we do that? We achieve it by only a single instruction, invalidate instruction. And this is an x86 instruction. Well, it means you can find it on Intel and AMD machines. This instruction flashes the cache without triggering a write back, so modified values in the cache, if not yet written back to the memory, are lost when you call this instruction. This sounds terrible, right? So basically, both Intel and AMD suggest that do not use this instruction when memory coherence should be considered. And there is already a safe version of this instruction, write back invalidate, as the name implied, write back everything inside the cache. So before invalidating the cache, so everything is preserved. However, as security researchers, we do not follow the menu that easily. I mean, obviously, we can cause a memory corruption by this single instruction. But why haven't we heard about any vulnerability with this invalidate instruction? Well, it turns out this instruction is a privileged instruction, and it means only privileged user can execute it. And then it makes sense, right? Because as we know, a privileged user cannot be malicious. Well, that's true, but this was the case only until the introduction of trusted execution environment. So since 2016, chip vendors have introduced a new hardware feature, trusted execution environment, TEE, to enhance cloud security. And on AMD CPU, it's called SEV, Secure Encrypted Virtualization. So before trusted execution environment, as a cloud customer, you have to trust the hypervisor to not leak your memory, your data, because you are literally running your code and the data inside someone else's machine. And after the TEE, you can protect your data even if you don't trust the hypervisor. So SEV assume that the hypervisor could be malicious or compromised. So basically, SEV assigns an AES key to each VM and encrypts the VM, entire VM by this key. And this key is only managed by the hardware, but not the hypervisor. So the hypervisor cannot read or write any content of the VM because they are all in ciphertext. And so, however, security is hard to implement. So AMD has to improve this feature over the past year. So with SEV-ES, the second version, they finally achieve confidentiality and finally bring integrity in the newest version of SEV, SEV-SNP. And that's the point where people consider SEV to be secure in the end. However, CacheWarp break it. So next, I will show how we exploit invalidate instruction with precise control, because trust me, you don't want to execute invalidate without care, because you are likely to crash your machine, because invalidate instruction invalidate everything. So you are highly likely to drop some unrelated content from other process or from other cores. So aligned with previous work, SGX step and SDV step, first we clear the present page of our VM's pages so we can identify a code pattern at a page granularity by the page fault handler. And next we can achieve single stepping by using the API-C timer. So there is nothing new yet. What's new here is that we can use write-back invalidating instruction, the benign instruction, because unlike SGX, SEV is a VM-based trusted execution environment feature. So every time we interrupt the VM, the hardware has to perform an entire context switch, which is affected by the cache state a lot. So with write-back invalidate instruction, we can make sure that every time before the interrupt, the cache is always clean, so we can get a reliable single stepping. And second, with write-back invalidation instruction, we can write back all the stuff in the cache. So before we arrive the correct point that we execute invalidate instruction, we are less likely to drop some unrelated content. So give us more reliable performance. And beyond single stepping, we can also perform prime and probe technique, like we selectively perform prime and probe on some cache sets, and then we can make sure that those values in those cache sets will be written back to the memory at first, so we are not going to drop them with invalidate instruction. So now we have a precise control framework, and what can we do next?
So at this point, we can drop memory at any time in our program. Let's build a full chain exploit with that. So the first exploit is really simple. We want to attack sudo, and sudo has a variable that's initialized with 0, and if it stays 0, we just win. There's no password check, and we just become root. So with CacheWarp, we just drop this right, invalidate it, value stays 0, we win. Here's the issue. So we will be never this lucky again to just get a win variable. So we need a more generic exploit primitive. And that's the idea of time warp. With time warp, basically, instead of targeting some variables in the program, we target the control flow. And so what we want to do is when a program writes a return address on the stack, we invalidate that and reuse the stale return address to warp back in time. Here's a high-level overview of what we try to achieve here. But here's a toy example. So if A is equal to B, we win. But A calls a function ret1 and B calls a function ret2. They will return different values and we don't win. What we do here is we call invalidate when ret2 tries to write the return address on the stack, and this effectively injects a new line of code where A will be ret2. Both values will be the same and we win. Here's an animation to explain. On the left side, you see our code. If A is equal to B, we just win, but A will return 10 and B will return 30. This is the assembly code. Now let's step through it. So first we call ret1. This will set the return value to 10, and we will return from the program and write this value into A. Then we call ret2, and here's where the magic happens. We invalidate when the return address, so it will reuse the stale return address. Now the return value will be 30. We will return from the program, and 30 will be written into A. Now the program continues normally. So 30 will be now written into B. And now both values are the same, and we call our win function. Now on the left side, you see a very familiar pattern. This is a simplified code of the SSH password login. And so if both values are the same, we got logged in and get code execution. Now, at the second function call, we trigger invalidate, which, as we saw, will inject effectively a new line of code where now the real password will be the hash of our user input. Test password will be hash of our user input. They are both the same. We win. And now, back.
Okay, so to summarize our paper, we are the first attack performed full chain exploits against SEV-SNP VM, and we achieve it by gaining remote code execution and privilege escalation. And this is only caused by a single instruction abuse, invalidate instruction. AMD has patched our vulnerability via a firmware and microcode update. And also we have open sourced our code on GitHub, and there's some exploit demos on our website. And there's also a blog post available for more details. So if you want to know more details, please feel free to check them out. Thank you.